Today we're going to be looking at section 3, which is more about vectors. So the last lesson was just kind of a review of what vectors are and how they work. Today we're going to start doing calculus on the vectors. We're going to be working with vector-valued functions, which is typically how we will see them in calculus, where each part of the vector is a function, not just a value, not just a number, but they are both actually functions of usually time, which means that writing a vector is really just like writing a parametric equation. It's just putting it together instead of specifically saying that x equals this and y equals this. And the x part of the vector is the x equation and the y part of the vector is the y equation. And if you think of them that way, then this lesson is going to be pretty much the same thing as lesson 1, which was about how we deal with parametrics. So that's how I always process it, so I'm not learning something new. It's just a different notation, that we're writing it in vector notation instead of writing it in parametric notation. But we're doing the same thing with them. To do this, says that we have a vector that we call I, which is 1, 0, so it's just an x component, and a vector j, which is 0, 1, so it's just a y component. And then what we can do is write any vector which has an a and a b part as ai plus b times j. The a is just the x component part, and the b is just the y component part. So what this is going to look like with some points is if I have a point, -1, 5, and a point, 3, 2, and I want to write the vector PQ as a combination of I and j. What I would want to do first is find that vector. So if P is -1, 1, 2, 3, 4, 5, and Q is 3, 2, I'm looking for that vector, which goes down 3 and over 4. So that's how we get our component vectors, by shifting or translating our vector so that it begins at the origin. And then this vector would be 4, -3. And if I want to write that in terms of I and j, I would say that it's 4i minus 3j. I is just the x part of the vector, and j defines the y part of the vector. Okay? So then we're going to look at calculus on these things. So the first thing that we learned in calculus was limits and continuity. It says if r is some function times I plus some function times j, then what we can do is just take the limits of the two functions, and that will be the limit of the whole vectored valued function. Then you take your limit of the x part and you take your limit of the y part, and that's just going to be your limit, is those two individual limits. As far as continuity goes, if both of them are continuous, then the whole thing is continuous. If either of them has a problem, then it's a problem. Okay, so one being continuous is not good enough. They either both need to be continuous or our final is discontinuous. So some examples on that. If r is cosine of ti plus sine of tj, then what is the limit as t goes to pi fourths of r of t? So we're going to then take the limit as t goes to pi fourths of cosine of t I plus sine of t j. Our first strategy in evaluating limit is just plug it in, and unless we end up with an indeterminate form, that's a really good strategy. So if cosine, if t is approaching pi fourths, then cosine of pi fourths is
1 over square root of 2.
1 over square root of 2. And the sine of pi fourths is 1 over the square root of 2.
Okay. I'm still waiting for the surprise.
For points of discontinuity, if r of t is equal to t cosine of t I plus t sine of t j, we want to say, where is this thing discontinuous? Because it's usually easier when we talk about the continuity of something to say where we have problems and then say it's continuous everywhere else. So where does this thing have problems with continuity? So is t cosine of t, does that ever have a problem?
No. Oh, like an error?
Yeah, like would we ever get an error in that?
No.
Okay, cosine it exists everywhere. Multiplying it by a number will still have it exist everywhere.
So
Sine exists everywhere. Times a number will exist everywhere. So this is continuous. It's just fully continuous. If our function is 1 over t I plus sine of t j, where will r have a problem?
0.
If t is 0. And even though it's okay for the one part, because it's not okay for the other part, it's not okay. Alright, so a problem with one component creates a problem for the whole vector. So at t equals 0, we have a discontinuity.
Plus anything, would be plus 0 is still
So the next part looks at derivatives. Specifically, when we think about derivatives, we're usually looking at a motion example when we're talking about a vector, because a vector typically describes a position of something, and so then as we take derivatives of that, we're working with motion. So the derivative of position is velocity. So when we take our derivative, we're going to take our component-wise derivatives. So take the derivative of the x part, take the derivative of the y part, just like we did for parametrics. So if you think of these things as just kind of a fancy parametric, then we're working with the same stuff we already worked with in section 1. So when we take the derivative, we're just going to take the component-wise derivatives. The first derivative is going to give us velocity. We defined speed as being the absolute value of velocity, which when we were dealing with functions before meant just make it positive. So if the velocity was negative 50, the speed was 50. But when we talk about vectors, absolute value means something a little bit different than just make it positive. What does absolute value mean?
Length.
The length or the magnitude. So our speed is going to be the magnitude or the length of the vector. Acceleration is going to be the derivative of velocity, or the second derivative of position, just as it has been for us all along. We're just going to take them component-wise. The direction of the motion is going to be the velocity divided by the magnitude of velocity, which would just tell us which way we're going then, because those, if we think about like functions, they would be the same, except one would be positive and one would be negative. That's not going to be the truth here necessarily, because magnitude doesn't mean just make it positive, but it's that same idea. It's an extension of that same idea. Velocity then is speed times direction. Those last two, not major concerns, but knowing that velocity is the derivative of position and acceleration is the derivative of velocity, and most importantly knowing that speed is not just make velocity positive.
Speed is negative.
Okay? Speed is the magnitude or the length of the velocity. That is very important. So if r is 3 cosine of ti plus 3 sine of tj, and this gives position, part A of this example wants us to find velocity. So velocity is the derivative of position. So the derivative of 3 cosine of t is
Negative 3 sine of t.
negative 3 sine of t. We get the I. And the derivative of 3 sine of t is 3 cosine of t. And we've got the j. Acceleration is the derivative of velocity. So the derivative of negative 3 sine of t is
Negative 3 cosine t plus negative 3 sine of t.
Alright, so just as it has been for us all year, velocity is the derivative of position and acceleration is the derivative of velocity. When we have two parts to it, just take the derivative of the two parts.
When we do
Um,
this, we don't do the parametric thing where we divide it by the.
No, because since it's a vector, we're leaving them both in terms of time, not in terms of x and y. Yep, so in parametrics, we would need to divide them so that we have it in terms of x and y. So we could plot it on a coordinate plane, but here we're thinking about two separate valued functions. The next part wants us to find, let's see, that's not what I'm going to do. Wants us to find the velocity at pi force, the acceleration at pi force, the speed at pi force. It also asks for the direction of motion, but again, that's not really a concern. I've never seen that show up on an AP. But velocity, acceleration, and speed, yes, for sure. So to find the velocity at pi force, we're going to plug pi force into our velocity function. So what is the sine of pi force?
1
Over square root of 2. So we're going to get negative 3 over square root of 2. And what is the cosine of pi force?
Stop.
1 over the square root of 2.
Wait, what's the square root of 2 from?
Plug in the pi force in.
Isn't it 2? No. Yeah. No.
It's square root of 2 over 2
Okay.
if you want to
Yeah.
rationalize, but I
Yeah.
don't rationalize.
You're not a rationalizer person.
I'm not a rational person. It's just true on so many levels. Acceleration.
Get real. Be rad.
I'm going to plug the pi force into the acceleration function. So I get negative 3 over square root of 2 I and negative 3 over square root of 2 j. Speed. You do not just take the velocity and make it positive. Okay? Speed is a number, not a vector. Speed is the magnitude or the length of the velocity vector, which comes from our Pythagorean theorem. The square root of the stuff squared.
If you were to have like a three-dimensional vector, how do you find the magnitude of that?
Still
have
Pythagorean,
another-
you just have another one.
just
Yeah,
have
it actually
another
works to just
square root
extend
of that.
it.
Okay.
That if we have a z variable, it does continue on out, which is a little bit weird to think that you could just do that, but it does.
Yeah, it seemed weird when I thought about it initially. And I don't remember the IJs
would
and
be a
Ks
bad
are.
job.
I was just trying to think of the difference.
Squaring something just makes it positive. So I end up with 9 over 2 for both of them.
3 square root of 2 over 2.
So
Yeah.
square root of
Why don't you
9,
be stuck in 0 for the speed?
which is
What?
Why did the Pythagoreans do it?
Speed is a magnitude of velocity.
Yeah, Travis is right.
First, or just 3. Ignore how many fingers I'm holding up.
So,
Wait, it's 3.
I get 9 halves plus 9 halves, which is 9, and the square root of 9 is 3. So the speed is 3 on this. Speed will always be a positive value because it comes from taking a square root of something. So we will always get a positive answer, but it is not just make velocity positive.
And
Okay? It's the length of the velocity vector.
in this case, does it just not have a unit?
Does not have a unit.
Yeah.
Yeah, we weren't given any units in the original problem.
That feels so wrong. Speed
So-
3.
3. Yeah, we weren't given any units.
How fast are
So
we going?
3.
Do what?
now, I don't know that I have ever seen the AP test use the I and J notation. That's not to say they couldn't. It's definitely a valid notation. But what I have seen them do more often is instead of writing it like this, they will tell you that R of t is, in vector form, 3 cosine of t, 3 sine of t. You do exactly the same thing.
Yeah.
You just write it in vector form instead of writing it with i's and j's. So velocity would be negative 3 sine t and 3 cosine t.
If we wanted to change it over, would that be
On a free response, that's fine. Either notation. I've seen this more often on multiple choice, I guess. And then
then
negative 3 cosine of t and negative 3 sine of t. So you get exactly the same answers. You just don't write them with the I and the j. You write them in their vectored format. Then if I wanted to do velocity of pi fourths, we're going to get a vector answer of that. Negative 3 over square root of 2 and 3 over square root of 2, etc.
If you were to put into the IJ form, would they mark you off?
On a free response, that's fine. I've seen these more in multiple choice.
Okay.
And then be careful with this. Okay, a lot of times I can say speed means magnitude, speed means magnitude, speed means magnitude, and you get that. But then when you see this absolute value, students just take velocity and make it positive. Okay? Absolute value doesn't mean just make it positive. That works when all we're working with is plain numbers. But what it really means is distance from 0. And since we're talking about component vectors, we're talking about then the length of the vector. So this would be that speed answer of 3. So be careful with the symbols of absolute value. Absolute value does not mean just make it positive. When we're working with real numbers, that works. When we're working with imaginaries or vectors, that doesn't work.
Yeah, remember when we worked with real numbers?
That glorious time.
Remember when the majority of our work was with numbers? Yeah. No, I don't remember that time.
when was this?
I see it times 14.
Freshman year?
That seems like a long, no, not even freshman year.
Yes.
I don't remember that.
Because we still had like,
Middle school?
it was middle, it was the 7th grade for me. No, it was the 6th grade, I think, or 5th or 6th grade when I stopped using numbers and we numbers we started using x's. And we're just like,
Algebra was so easy for me because I already was basically doing that in elementary school. And it's like 3 plus blank box equals 6. 3 plus
All right, this is a position.
minus 3.
yeah, stuff like that, but we never call it x.
This is a position. Part A of this question wants us to write an equation for the tangent at the point where t equals -1. What do we need to write an equation of a tangent line?
Slope, point, slope.
A point and a slope. All right. I find this problem easiest if you think about it as a parametric equation. That x motion is being defined by the I part of this vector, and that y motion is being defined by the j part of the vector. So then if I need a slope, I want to think about parametric slopes. And for parametric slopes, we need a dy dx. So I get 3t squared minus 12 over 6t squared minus 6t. I could simplify that down, but it doesn't really matter because what I want to do is now evaluate this at the time given, which is -1.
That's disturbing. Time is -1.
Time is -1.
What was it a minute ago?
1 unit of time before the problem started. And so
He's there now. Where was he a minute ago?
that's not right.
It's still right
I
there.
subtracted wrong.
I thought you were putting it down the out.
There we go.
That's fair. Because his motion is 0.
And I can reduce that down then to -3/4. So that's our slope. What else do we need to write an equation of a line?
Point.
A point. So we need to take our time and plug it into x and y. So let's see, that's -2 minus 3, so -5. And plug it into y gives -1 minus 12, -13. Nope. It'd be plus 12.
And this is a vector tangent to it, or a line?
This is a line tangent.
Alright, then y.
So then y equals mx plus b, or point slope form. Y minus y1 equals mx minus x1. Or if you are more comfortable with y equals mx plus b, by all means at this point in the year, don't start doing something new. Do what works for you. Okay, so if you're more comfortable with y equals mx plus b, that's totally fine.
Slope is so much easier.
Oh,
What would the y
it's
equal
more
supposed to be of that?
memorization, but it's easier to forget.
It would be -3/4 x plus 29 over 4.
Is that 24 over 4?
29 over 4.
I'm very much a point slope guy.
Part B wants us to find the coordinates of the points where the horizontal component of velocity is 0. All right, find the coordinates, so that means find the x and the y of the points where the horizontal component of velocity is 0. What is the horizontal component of velocity?
X.
Of velocity?
Well, the derivative of x.
The derivative of x. So dx dt is our horizontal component of velocity. So horizontal motion is defined by our x variable, and then velocity, we want the derivative of that. We want to know where this equals 0. So that is time 0 and time 1, but that is not the answer to our question because it wants us to find the points where this happens. So we need to plug those into our x and y equations. At time equals 0, we get the point 0, 0. At time equals 1, I get the point -1, -11.
Why is it up there for y equals -1? Why is it -11?
Is it supposed to be positive?
Yeah.
Did I add wrong?
No.
Yep.
Yes.
I added wrong like 3 times. It should be positive 11, which means this should be negative.
Okay. I'm still confused.
Where?
Isn't it?
Yeah, no, just plug in a -1 to the top.
Oh, for -1. I thought you
Yeah.
were talking about 1.
No.
No, he was talking about back in my
Yes.
blue work.
I agree with that.
Back in my
Yeah,
blue work,
I
I did
was-
it wrong.
I was still so checking my work, I just hadn't even gotten to the green stuff yet.
The y equals mx plus b is still right because I just stole that answer from the book. I didn't try to do my own arithmetic there. So that answer's still right. When I try to do my own arithmetic, things go wrong. So. As far as taking derivatives, all the same rules apply. As far as if you need to do product rules or quotient rules or chain rules, you just do them individually on the 2 components. But anything that you would normally need to do for a derivative, you're going to do, you just do it to both components. As far as integrals go, take the integral of the components. And remember plus c if we're not evaluating the integral on a certain interval. So if I wanted to find the integral of cosine ti minus 2tj, I'm just going to take the integral of each of those pieces. So the integral of cosine is
Sine.
positive sine. And the integral of 2t is
1/3
T squared.
t squared.
T squared. Nice catch, Kyle.
And plus a c. Technically, they both need a plus c, but we can combine that together and make it just 1 plus c.
Love that rule.
If we wanted to do this same problem over an interval of, let's say, 0 to pi,
Just plug it in.
we would integrate component-wise. But we don't need a plus c. And then plug in upper. Minus all of, be careful that we're going to subtract all of, plug in lower. Sine of pi is
0.
sine of 0 is,
0.
and double negative, so plus, but it's still 0. So I end up just having negative pi squared j. If there weren't so many zeros, you'd want to combine like terms. So combine your I components together, combine your j components together, so that you just have an I, j answer. But here we end up with a lot of zeros. But you would want to combine together like terms of i's and j's for a final answer.
Wait, where did the C go on the when you started the blue work?
If we have limits of integration, we don't need a plus c. We plug in upper limit minus lower limit. Okay?
When do you solve for c again?
If you're given an initial point.
That's right, yep. Okay.
Wait, dude, guys, what?
All right, that's the end.